We're talking to you about the electrification of planes, trains and ships. It's an initiative that we're calling PROPEL-1K, PROPEL for Pioneering Railroad, Oceanic and Plane Electrification, 1K because we've set aggressive targets of 1,000 watt-hours per kilogram and 1,000 watt-hours per litre in terms of energy density. I'm your host today. My name is Halle Cheeseman. I'm a program director at ARPA-E. I've been with ARPA-E for almost 3 years, and I spent the 37 years before that working on energy storage systems, mostly batteries and some fuel cells. We want to be very clear throughout this presentation that this information that we will be sharing with you does not constitute a funding opportunity announcement. No FOA exists at this time. 2 slides just to introduce ARPA-E to you. Most of you, I'm sure, know ARPA-E. Founded in 2009, stood up under the Bush administration and then funded under the Obama administration. We've enjoyed good bipartisan support throughout our history. We are the Advanced Research Projects Agency for DOE, and as such, we work on early stage R&D. And by definition, we embrace more risk, perhaps, than other agencies are able to do. We're looking to solve hard problems, and we don't expect every project that we fund to be successful. We are funded, of course, ultimately by the US taxpayer. So, we're targeting improving US economic prosperity, national security, and environmental well-being. In terms of some awards out there, our awards tend to be smaller. An average award might be somewhere between $3 or $4 million, and for a period of 3 years. We have mission statement or goals, and when we were started, reducing imports, improving efficiency, and reducing emissions were 3 central pillars of what we were going to go and try and work on. Certainly, when we talk about PROPEL-1K, it touches each of those 3 mission pillars. We had 2 other pillars added to us more recently. Probably PROPEL-1K doesn't relate to them. Taking up less room on this chart than maybe it deserves is goal 2, and that's ensuring that the US maintains a technological lead in developing and deploying advanced energy technologies. And I don't think I'm giving anything away by saying that in terms of energy storage, we have in fact got some catching up to do, having lost some chances to be a leader over the last few decades. So this is what we're going to be talking about. Zero emission electrification of heavy duty transportation, planes, trains and ships. We have EVs, right? 100 kilowatt hours maybe in terms of energy storage. Some of the trucks that are being considered up to 1 megawatt hour of energy storage. Planes, trains and ships require a lot more than that. As we look at those applications, we have to start with safe. Safety comes first, and we'll talk about what we think that looks like and how that might be different from the lithium ion that's been developed over the last 20, 30 years. We're looking for transformation energy storage, 5 times better in terms of energy density than what currently exists, and even 2 to 3 times better than the lithium metal, solid state, silicon anode work that we expect to be installed by the end of this decade. We're looking for 1,000 watt-hours per kilogram and 1,000 watt-hours per litre at the net system level. So not at the cell level, not at the fuel cell level, but at the total system level. We're also looking at that performance level being available at the end of life, not just at the beginning of life. We've been on this journey now for 15 months, and we've talked to lots of people, and we've been able to pull from that promising technology strategies and approaches that we think could get us to these lofty goals. And we'll be talking a little bit about some of those strategies and approaches that we think have promise. A little bit hokey to say it, but this is an opportunity to reinvent transportation as we know it. And if we look back through the whole history of batteries, since the beginning of lead acid, energy storage innovation has been able to enable new applications and new uses and even new industries. We wouldn't be ARPA-E if we didn't focus on the costs of what we're working on here. So techno-economic analysis leading to levelized cost of storage targets is a key part of what we're going to be sharing. And the three key things we're going to be sharing today are our objectives in this initiative, possible metrics that we think are valuable to express achieving goals with this initiative, and finally, deliverables, a roadmap, if you like, of things that would have to be seen in a project should projects be requested at some point. We had to include this chart. This is EPA data. Transportation, 29% of US emissions. We've done a great job the last 10 years working out how we can electrify light-duty vehicles. And there's a lot of work going on medium and heavy-duty trucks, both with batteries and fuel cells. In this initiative, we're trying to tackle the tough stuff: aircrafts, rail, ships, and boats, and even some of the other relating to agricultural and industrial vehicles. These are hard targets, but targets we should pursue if we're really committed to reducing greenhouse gases and if we want to get to that net 2050 target. It all started with what we call a fast pitch. Many of you would have been to an ARPA-E summit. We had one in 2022, and during these summits, we get an opportunity to ask questions. So gave a presentation in May of 2022, and we asked the question, if we had something that could deliver 1,000 watt-hours per kilogram, what could we do with it? And you can see in the chart on the left, the analysis that we had done said, if we took today's energy storage that's in an EV, we don't really get very much of interest when we stick it in a plane. But if we could get to 1,000, we could have something that could carry 100 passengers, 750 nautical miles. That includes a 19% reserve. So if you've put the reserve in the mix, we're talking about a range here of up to 1,000 miles. As part of these fast pitches, we asked people to come and talk to us. No surprise, lots of people came to talk to us about, hey, this 1,000 watt-hours per kilogram, it sounds good. When can we have it? We also had lots of people come and talk to us about possible solutions. Over 30 different groups, companies, organizations, universities have talked to us about ideas that make us believe that this might be achievable. At the fast pitch, we threw down a gauntlet. We said, hey, if we started considering metals as electrochemical fuels, we have a lot of energy density to play with. Jet fuel, 20 kilowatt-hours per kilogram. Lithium as a fuel is actually 11. And even in its oxidized form is still way above our notional 1,000 watt-hour per kilogram target. So never has this question been asked so broadly or as loosely as in the green box here. How might we package these metals to deliver these battery 1K or fuel cell 1K targets? As we said at the beginning, this is about big applications that need a lot of energy and in some cases, a lot of power. So here's a chart of motive power in megawatts versus energy in megawatt hours. And we're plotting on here different groups of vehicles and vessels. And this is really where we are today. So passenger EVs, 100 kilowatt hours, need, several 3C, 4C for acceleration. You can see in the very corner of this red square is where Class 8 trucks need to be in terms of 1 megawatt hour of energy storage. And then you can see a whole host of other vehicles, vessels, and aircraft that need a lot more. And so in simplicity, the PROPEL-1K is targeting this space, targeting the green space in this green square. You can see nearly everything involving locomotives is in this green square. A lot of interesting aviation applications are in this green square, and even a lot of the shipping that operates within the US territorial waters. I wouldn't say that 100 megawatts hours is the limit, but it is the focus of what we're interested in as far as this initiative is concerned. Let's start with safety. I talk to lots of people about EVs. I have an EV, and I ask people, well, what would make you consider an EV? I hear a lot about, well, we need faster charging, and we initiated a program on that last year. I also hear people say that they worry about safety, and would there be enough time to get out of the vehicle should there be a problem? And I believe that there is. But when you start talking about planes and ships, you're talking a lot longer time is necessary if you want to evacuate those vessels or vehicles. So we all know about thermal runaway. We all know that one chemical reaction leads to another chemical reaction, leads to another chemical reaction. And before we know what's happened, we have a sequence that's getting carried away, and we've got very, very high temperatures and conflagration. When we look at solutions in this space, we can't have thermal runaway. For sure, we're going to be packing energy into small spaces, but we can't have the kind of sequence that we see and we've learned about with lithium ion. I'm going to go through all of these in detail. Some of them are relatively self-explanatory, but I will mention shutdown safety catch mechanisms. Is jet fuel safe? Jet fuel is very safe if you don't bring a spark or a flame to it. And as we think about strategies and solutions to solve these challenges for transformational energy storage, they're the kind of things we're interested in. So just like a gun has a safety catch on it, that gun remains relatively safe as long as that safety catch is in place. And they're the kind of things that we're interested in terms of potential solutions for planes, trains, and ships. So planes, trains, and ships. PROPEL-1K, we believe, can enable regional flight on aircraft transporting up to 100 people. Railways, we believe it would enable total electrification of everything in the US. Unlike a lot of other countries in the world, we didn't get the opportunity to electrify our rails with third rails or with overhead wires. This is our opportunity to electrify the whole of our network without such a large capital investment of putting in an electrical cable system. Maritime, you know, I think there may be some people who disagree with me here, but we're not trying to tackle large container ships going across oceans, going between Shanghai and Los Angeles. But we do believe this possibility enables us to electrify all ships that operate exclusively in US territorial waters, ferries, barges, tugs, and Jones Act freight. And Jones Act freight is the freighters and small container ships that go from port to port along the US coast. And this would enable even electrifying those all the way to Puerto Rico. Trucks and buses, this initiative isn't targeting those, but that doesn't mean if we weren't successful, it wouldn't benefit trucks and buses. So if you were to take a 1 megawatt hour battery today and put it in a truck to give it 500-mile range, that takes up 20% of your load in terms of weight limit. And if you had PROPEL-1K, you could take that from 20% down to 5%. So it could be a benefit, but it's not the focus of why we're looking at this initiative. So objectives. We're trying to keep this not too long. We're trying to really do a sort of an open invitation here. You know, what are all the ideas out there that could lead to a zero emission and fossil-free transportation for planes, trains, and ships? We have to have uncompromising safety. We want improved energy efficiency because generally, when you electrify a propulsion system, you should see a substantial increase in the efficiency of that energy usage. Per the mission, we want energy independence and technology leadership. Fast turnaround time is important because all idle time equals lost revenue in these businesses. We want lower operating costs than current vehicles or vessels. But as I said, I've been in batteries for 40 years. I know this takes a long time. And so this may not be something that we see cost effective in the next 10 years. But by the time we get to the 2040s and we're really chasing towards that net zero goal 2050, we have to be enticing people here with compelling operating costs. We don't want manufacturing these systems to have too big a CO2 footprint of its own. So you'll see a specific metric in a minute, but we've targeted that to be comparable with automotive EVs in terms of the CO2 generated when we make all of the materials required for EV batteries. And finally on this list, supply chain circularity. You need to know this is an area of interest for ARPA-E at the present time. I have a colleague, Laurent Pilot, who's working on this. And this isn't about recycling. Recycling is the circularity course of last resort, taking a battery or a fuel cell and mashing it all up and starting again with the core elements is not what circularity is about. It's about building into the design and development of energy storage systems a way to gain value by reversible manufacturing, reactivating, and not destroying all the value when that battery or fuel cell comes to the end of its designated life. So here's some numbers for you. Zero carbon dioxide, NOx and SOx. Emissions in operation is the key greenhouse gas emission. You will notice that water is not included here. So it's about zero CO2, NOx and SOx. Target system size, 1 to 100 megawatt hour. Doesn't mean it wouldn't benefit more than that or less than that. Gravimetric system energy, volumetric system energy, 1,000 watt hours per kilogram, 1,000 watt hours per liter. That's a net, right? That's at the system level, not the cell or fuel cell level. It has to be the whole system. And we know it's hard and we know it's risky, but that's the kind of stuff ARPA-E does. 30-minute turnaround time. Certainly planes and trains will need the 30-minute turnaround time to remain reasonable businesses. What will that involve? It could involve refueling. It could involve recharging, reactivating. It could involve swapping batteries in and out in order to achieve that 30-minute turnaround time. Less than 100 kilograms per CO2 of kilowatt hour nameplate system energy density, energy capability. And finally, energy efficiency in use has to be 70% or greater. What we're really saying there is we don't want to waste 30% or more as heat, and consistent with driving for improved energy efficiency and the benefits we believe should come with electrification, we have a tough target there of 70% or more in terms of the energy efficiency in use. That's not round trip efficiency, that's the energy efficiency in use. Those 7 metrics apply equally to all 3 applications that we're interested in. These 2, you can see the emergence of 2 different tracks. So 8, you'll quickly appreciate, relates more to a fully battery electric airplane. 1 kilowatt per kilogram, that's like a 1C for 3 minutes. That's the peak power capability, and that is what would be required for a plane to take off, needing typically 3 or 4 times more power for takeoff than it does for cruise. It needs that power capability when the energy storage system is full, but also towards the end of its state of charge, when perhaps the plane is coming in for land and has an aborted landing and has to go around again. Continuous power capability there is like a 3-hour flight with enough for reserve. So C over 4, if you like, in terms of a rate capability. LCOS, 30 cents or less per kilowatt hour. We spent a lot of time working through what we think these numbers should be to be appropriately competitive. And that's the number that we came up with aviation. You will find that we're not going to specify cycle life or calendar life. That will all get generated in the LCOS calculations that you would do if you have interest in this area. No point putting lighter weight batteries or fuel cells on a plane if you have to have tons and tons of cabling. So system voltage above 1000 volts is what is going to be necessary, we believe, to make this all work ultimately. So that's more planes, I think you would agree, and 9 is about more trains and ships, but could also apply to hybrid planes. so a much less lower peak power capability, C over 4, for 15 minutes though, trains going up hills or accelerating ships. Continuous power capability, C over 10, and then you have an LCOS here, which is lower, partly because the cost base for these applications is lower, but also if you don't need the power capability, you have opportunity not to have such maybe expensive materials. Okay, so that was about metrics, and we tried to keep them as short and as sweet, or maybe not quite so sweet as possible. Let's just talk about why we believe this may be possible to achieve. If you look at the history of batteries in general, or certainly lithium-ion, we started with small cells and we sort of worked to improve their capacity, and then we welded them together to make battery packs to go into computers, and then eventually we worked out how to put 6,000 of them together to go into some of the first EVs. Then we put them into battery pack boxes, and then we started putting those battery pack boxes on racks to go into storage containers for grid energy storage. So lots and lots of boxes, sort of the nesting dolls of packaging, from active packaging, where we take the active materials and package them, if you like, with conductive additives and binders and coatings maybe, all the way through to eventually integrating it into a structure involving anchoring and crash protection in the actual vessel or vehicle itself. And so we're almost saying, well, don't think no boxes, think maybe don't think so many boxes. So as per the nesting dolls, if we look at the end and start with where we want to go, can we take out some of those packaging steps, or do we have opportunity to integrate some of them together so they don't take up so much energy density real estate? Start with the end in mind. And here are 8 strategies. As I said, we've talked to over 30 folk over the last year. 19 of those came and gave very brief presentations at the workshop we held in May. I believe some of their material is available on the ARPA-E website, and there's a link to that later. So we pulled out of all the conversations we had 8 strategies, and these may be of value individually, or indeed they may be of value if you combine them together. So mechanically rechargeable, we're used to electrically rechargeable. Fuel cells in some ways are mechanically rechargeable, but the example we're showing here is a zinc air battery that was developed by a company called Electric Fuel. They had electric buses and post office vans running around Europe where there was a zinc cartridge in a zinc air battery. So when the zinc was exhausted, that cartridge was pulled out, replaced with a fresh zinc cartridge, and the zinc oxide of the old cartridge was regenerated or recycled in some way. I can't buy into swappable batteries for passenger vehicles in the US. I understand they're becoming implementable in China, but certainly for these applications, there's no reason why we can't have swappable energy boxes or swappable batteries or swappable fuel cell systems. But fuel cell systems probably leans into the third picture here, separating power and energy. It could be a fuel cell system, or it could be a flow battery system. We all know that flow batteries are low energy in terms of the catholytes and analytes, but how about high energy dense electroactive slurries? Or could we even have liquid metals? So that's the idea behind 3. Let's not carry the catholytes with us. So metal air batteries, fuel cells, even metal seawater or metal water, external catholytes. We could gantrify the solutions. This is a word I've been trying to popularize. Essentially, it means combining a mechanical structure with electrochemical function, and we're seeing that a lot now in passenger EVs. Revisiting the past. I've been with electrochemical energy storage for as long as I have, because I know of all the problems that they can suffer, but new technology is being developed all the time. And we can take that technology sometime that exists today, that didn't exist yesterday, so we can apply it to problems that couldn't be solved in the past, so that we can be successful in the future. Good example of that would be revisiting some of the chemistries we've written off as only primary, just do enabling technologies exist now to make them rechargeable? We strap jet engines to wings. Those jet engines run at 1500 degrees C. We shouldn't be so scared of running at high temperatures. We have grid scale batteries now, sodium sulfur, sodium nickel chloride, and calcium antimony that run at high temperatures. And that's something we should consider for transportation energy storage systems. And finally, hydrogen storage. When you look at these applications, particularly those where energy density is important, some of the ways you might think about hydrogen storage may not get there, but there are other ways. Hydrides, goops, slurries. I've seen all of those the last couple of years, and I think they have merit. Hydrogen is that pseudo metal, right? It's the gaseous metal. It gives electrons just as readily as some metals do, and that's certainly considered in the solution set here in terms of viable and strategies of interest. So here is a total list of all the areas of interest that may be pursued alone or in combination. A long list, which we won't go through here, but let's break it down. We've talked about many of these, in the last few slides. We think the solutions here are going to be batteries or fuel cells. We're certainly open to other things if they can achieve the metrics, but we haven't come across any in the discussions we've had the last 15 months. Uncompromising safety, we've mentioned that. Swappable batteries, mechanically rechargeable, platforms that separate energy and power. And I mentioned in passing pumpable electroactive slurries, goops, and even metals as part of the solution set that may have value to this initiative. High temperature, we mentioned external catholytes, revisiting the past, gantrifying high voltage systems. High coulombic efficiency, if this is to be a battery, as opposed to something you would consider to be refueling, maybe like a flow battery or a fuel cell, you're going to have high coulombic efficiency, we suspect, to get the life characteristics you need. This isn't about 2 nines coulombic efficiency, it's 3 or 4 nines. We think in order to verify that you can achieve high life, that you have low or degradation mechanisms that aren't going to kill you, that valid application of accelerated life test is going to be important. So it's an area of interest. In my experience, if you have a lot of compression or expansion, don't expect a lot of life. And so low compression, low expansion, or high dimensional stability, we believe, is going to be important, certainly for those battery solutions. Compact, safe, high energy dense packaging of non-hydrocarbon fuels. What's my definition of a hydrocarbon fuel? Anything that has carbon to hydrogen bond that you're expecting to be a fuel as a solution. Don't give us proposals involving carbon hydrogen bonds as a fuel. We will not have interest in that. High efficiency systems, I talked about use efficiency. This really relates to round trip efficiency. How much energy do I have to put in and how much energy do I get out? So high efficiency systems in that respect. And finally, hybrid configurations, that's there. Is there a high power plus a high energy combination that you could contemplate that would meet the overall metrics at the system level? Certainly interested to hear those. Be careful that when you propose them, in addition to 2 good things, you're not bringing the combination of the bad things as well. So we're thinking that we would divide a possible program into 2 18-month phases. Both phases will have specific deliverables. We would want to sponsor as many teams as possible in the first phase. We know we're doing something hard here, and we want to flush out the things that aren't going to get to our goals quicker than not waiting till the end of 3 years to find that out. So here's the deliverables for the first phase. The first one is an important one. Experimentally show 1K performance at the chemistry level. When I say 1K, I mean the 1000 plus 1000. I'm going to explain a little bit what we mean by chemistry level in a moment. The second part of this would be to design a lab prototype. So experimentally show some chemistry and then design a module reactor or cell stack that's a 1 kilowatt hour benchtop laboratory pilot. Model a 1 megawatt hour system. It could be more than 1 megawatt hour, 1 megawatt hour mega minimum. Identify and project roadmaps and bridging strategies to achieve the ultimate goal. And a good example of that is separators on membranes, right? Well, initially I'm starting with 100 micron, but I believe I can develop it to be 20 micron. That's a good example of a bridging strategy to achieve ultimate goals. And there are lots and lots of examples of that kind of thing that you may not be able to achieve in the first 18 months, but you would certainly consider to be on your roadmaps for 3 years or beyond. Identify a valid accelerated life test. Deliver an intermediate techno-economic analysis and LCOS analysis. And finally, conduct a safety FMEA. You probably know what one of those is. Failure mode effect analysis. If you don't, there's lots of people out there who can teach you and even facilitate an FMEA session for your team. Here's a note. Phase 1 may include a critical go, no-go that will be used to justify requests for detailed phase 2 proposals. If we were to solicit proposals for this initiative, we expect more effort to be required for the first 18 months. And in reality, too much detail for the second 18 months won't be possible until you're well into the project. So for example, we might have a very critical go, no go to be achieved at the end of quarter 4. And then we would invite folks in quarter 5 to put in now detailed requirements for what they want to do in phase 2. That would be on an invitation basis based on the teams who were showing the most promise and the most compelling progress towards the 1K performance targets. Phase 2 deliverables follow straight from phase 1. Oh, here's the chemistry. Then we'll come to that in a minute. Here's the chemistry, right? Chemistry must include, if it's a battery, everything that's inside a can or a pouch based on typical batteries. If it's a fuel cell or flow battery, onboard catalyte, fuel analyte, membrane, electrode assembly, cell end plates. I think you get the spirit here of proving out a chemistry. Tank hardware prorated. So you have to include something about the tank hardware, but we will allow you to prorate that in terms of what it would actually be on a larger basis. This calculation does not need to include packaging, thermal management, safety containment, pumps, valves, pipes, other balance of plant or electronics. This chemistry must experimentally show energy capability, the 1K performance, but also at least some reversibility, whether that's refillability, recyclability or reusability. We expect at the end of 18 months to have gone through 10 reuses, cycles or refills with no more than 10% energy loss. That's a long, long way from where it needs to be eventually, but this we think is appropriate for early demonstration of capability. We're not asking for 3 minutes. We're only asking for 1/10 of that in terms of the option 8 track power metric, and 3 minutes, sorry, not 3 minutes, 1.5 minutes for the option 9 power metric. Second phase deliverables follow from first phase. So it's building that benchtop prototype that you designed in the first phase, right? And then designing a 1 megawatt hour system. So you model it in the first 18 months, by the end of the 18 months, and then you design it in the second 18 months. Continuing to improve chemistry and fine-hone those roadmaps and bridging options, developing credible life prediction, and so on. This is a spreadsheet or worksheet that would be in any request for proposal, should we get that far. This is the gravimetric one. There would be a volumetric one as well. So for the proposal, at a minimum, everything under the chemistry column down to row 8 would have to be completed. What's your anode? Milliamp hours per gram. What's your cathode? Milliamp hours per gram. Which one of those is limiting? And then take what the nominal open circuit voltage would be to get a theoretical watt hours per kilogram for just the active materials, really. But then there's all that supporting chemistry, separators, electrolytes, membranes, catalysts, how much does that reduce the energy density from 5? So you end up with 6, which is the nominal, sorry, 4, which brings you to 6, which is a nominal watt-hour per kilogram. But we all know as soon as you apply a current or pull a current, you're going to get polarization at the least. Maybe your Nernst equation is going to change your thermodynamic voltages. So what will your average operating voltage be at the continuous rate? That's the lower of the two rates, because that's going to give us an operational watt-hours per kilogram. The target is 1,000 watt-hours per kilogram. That's what needs to be in that box, or a number higher than that, based on applications that we would request. We would invite you to fill in as many boxes as on this table as you can. But it's the boxes in the first column down to row 8 that would be critical. As part of that 18-month phase 1, you would be filling in the boxes in the middle column. And as part of the phase 2, you would be filling in the boxes in the right-hand column. So this becomes a tracking chart for progress towards our lofty goals. And as I said, this is the gravimetric chart. There would be a volumetric chart also. LCOS, as I intimated at the beginning, levelized cost of storage is important. That's what's going to drive electrification in these applications. Does it make sense financially? So I would point you to two sources. One is the DAYS FOA. The DAYS was a long duration energy storage program launched in 2018, where LCOS was the key metric for grid energy storage. So that will help educate you if you read that in terms of how we think about LCOS. But PNNL also have a great methodology that you can go and find on their website per the link at the bottom, and that will tell you how to calculate LCOS. So 4 key components here: CapEx, operation and maintenance, consumables. The DAYS program, it was electricity that was the consumable mainly, but there may be materials. There may be single-use materials that are part of a potential proposal here. Hydrogen, as an example, which would be a consumable material and would go into the C consumable part of this LCOS calculation. And we would give you the assumptions for both electricity cost and hydrogen cost if there was a FOA issued, and they would be consistent though with reasonable DOE targets. So for example, 3 cents electricity, $2 per kilogram hydrogen. Finally, infrastructure here. Don't neglect infrastructure. If it's refueling, you need refueling equipment. If you're going to take off a container on a train, put on a fresh one, and then charge that other one slower, then you need something to be doing the moving, and that needs to be part of your infrastructure. Just like CapEx needs to include any additional inventory you need to operate a swappable battery system. So I mentioned the 2 targets there: 30 cents per kilowatt hour, 20 cents per kilowatt hour. They're the LCOS targets. So we're not specifying cycle life or calendar life. That's going to be driven by the LCOS. And so pay particular attention to that and justification for the numbers that you choose to use. This would be a good example of what an LCOS calculation output should look like for a heavy-duty vehicle. So you see here the 30-cent example, what CapEx could be, what O&M could be, electricity assumption 3 cents in this case, charging infrastructure 10 cents for a total of 30 cents. Okay, I have almost finished. You'll be glad to hear. I'm sure some people have left this call. We're going to get to this general Q&A in a moment. I did want to bring your attention to the information on this chart. We did publish on ARPA-E Exchange a teaming announcement on July 20th, so almost 3 weeks ago. This is an encouragement to say, hey, there might be something coming. Start talking to other groups and other companies to decide who you need to work with to achieve 1,000 watt-hours per kilogram and 1,000 watt-hours per litre. The website, sorry, the ARPA Exchange lists the links. You're not going to be able to access them on this presentation, but it lists these links that you're going to be able to access if you go onto ARPA Exchange. And this is information, the fast pitches I mentioned. It also gives you access to the workshop that we held May 7th and 8th, 9th and 10th, sorry, which some of you came to. Don't ask any questions, or we won't ask any questions on timing. But I will draw your attention to this statement at the very bottom of this chart. That was what was issued or was stated as part of the teaming partner announcement, and that has not changed. So now we're going to move to the general Q&A session. I hope we've been receiving lots of questions in the chat. I'm the program director for this initiative, and Apoorv Agarwal is a colleague. He's one of our tech-to-market advisors, and I believe he's been taking notice on the chat of questions that have come in that will be useful to everyone's understanding. We will continue to record the Q&A, so this will be available in the future for everybody to be able to access. As part of the registration linkage, we did offer one-on-ones. We opened up 48 slots, one-on-ones. And as of this meeting starting, we had a handful left. So if you want a one-on-one with us, it may still be possible. We want to ask individual or maybe more confidential questions in a one-on-one. And as I think everybody knows, should a FOA be issued in the future, we go into quiet time there, so we would not be able to talk to any of you. So there's still a little bit of time left to connect with us and ask questions, and we invite you to do that. We're very excited about this initiative. We're very positive about the transformational opportunities here. We are under no illusions that what we're trying to do is extremely difficult and very risky, but that's partly why ARPA-E was founded. And at the beginning of last decade, we funded a lot of projects related to range for EVs, and there's at least 6-8 companies who have been successful as a result of that, and who are developing technology that would help the US to lead. So with that, Apoorv, I'm going to hand over to you. I'm going to leave this slide showing Apoorv, and I'm going to hand it over to you to tell us if there are any questions.
Yes, thank you, Halle. Can you hear me?
Yes.
Perfect. Yes, we have received several questions throughout your presentation, and I will start asking them in groups, and I encourage everyone to keep asking their questions through the chat. We will keep monitoring them. The first few questions were related to the availability of the materials from this presentation. People are asking whether a recording will be available as well as the slides themselves.
The answer is yes to both. We will make both available, and I would guess they will be available in a couple of weeks.
Thank you. The next question is related to what constitutes the system of which the energy density targets are being set. So there are a couple of questions, and I'll read them verbatim. Could you elaborate what constitutes the kilogram at the system level of the battery system? What parts of the battery will be counted for this kilogram? The second question related to this is, for clarity, is it correct that the system for which the density parameters are specified is the electrochemical system that is intended to be a component of the power system propelling the train, boat, or train?
I'll try and answer that the best I can. It's supposed to include thermal management, system management for the energy storage system itself, so any temperature controls, any airflow controls. It's supposed to include the balance of plant that's unique to that particular energy storage system. It does not include the power electronics, but it does include the battery management system. So we try and use the word net here, because if, for example, the energy storage system can be made part of the vehicle or vessel, that's actually a subtraction, and you would have seen that on that spreadsheet I showed. So without the cabling that connects the energy storage system to the plane's propulsion system, it's supposed to be everything that's net to the plane, train, or ship.
Thank you, Halle. The next question is about any emissions that occur during operations. So how do we treat emissions are we talking about gas capture? Do we allow any emissions to occur during the manufacturing of the ESS?
We allow CO2 emissions per the metric that was put up, the 100 kilograms per kilowatt hour CO2 for the manufacture of the system. But during operation of the system in a plane, train, or ship, no carbon dioxide, NOx, or SOx emissions.
Okay, perfect. There are a couple of questions related to hybrid systems. One is, I've been talking to a major shipbuilder about hybrid electric propulsion system, and their biggest concern is fuel infrastructure as well as the hydrogen storage on a ship. Why wouldn't you look at replacing diesel generators with hybrid systems consisting of fuel cells and batteries running on diesel in the interim until the hydrogen infrastructure is developed, then switch to hydrogen as the final solution by 2050? The second question related to this is, great talk. Is the hybrid system an option if the hybrid system has the ability to make zero CO2 emissions?
Okay, so I think I can answer that question. We're under no illusions that what we're trying to do here is going to take a long time. So there's going to be many hybrid solutions that involve diesel over the next, let's say, 10, 15 years. We're really trying to develop solutions here for the 15 to 30 years, at which point we believe, hydrogen infrastructure, as an example, will be in place. So the way to think about this is, yes, there will be solutions in the interim, but we're looking beyond that with this initiative. And it's interesting, I think I heard that the Prius was launched, was it like 20 years ago today or something? That came in as a hybrid to show the way. But only now are we starting to see more and more fully electric vehicles. So we expect that same thing to play out. We expect there to be lots of hybrid solutions in the short term, but ultimately to have emission-free solutions, back end of the 2030s and forward.
Okay, thank you.
What was the second question again? I'm not sure if I asked.
Yeah, sorry. Second question was, is the hybrid system an option if the hybrid system has the ability to make zero CO2 emissions?
Yes.
Yes. All right. Another question is, even considering all elements across the periodic table, none of the electrochemical systems have even theoretical densities of 1000 watt-hours per kilogram or liter, except a few metal air systems. That will rule out all other systems listed. Comments?
Read the first part of that question again.
Yes. 1 second. Even considering all elements across the periodic table, none of the electrochemical systems have even theoretical densities of 1000 watt-hour per kilogram, except a few metal air systems.
But I will say that's not my understanding based on the conversations we've had with lots of people, and certainly looking beyond metal air systems to other solutions. So that's not our understanding based on the research we've done.
Okay. Next question is PROPEL-1K looking for complete systems, or could we propose a subsystem? We are developing a greater than 1 megawatt hybrid electric jet engine that would use SAF as the fuel source. We do not make the batteries to store the energy. Do we need to find a teammate to submit to the potential initiative?
Well, ultimately, it's going to be driven by the metrics, right? So we believe in SAF. We believe that's a solution, but that's not part of this initiative. There's other colleagues of mine who are working on that, but anything that involves hydrogen carbon bonds is not within this particular, is not of interest to this particular initiative.
Okay. What if we burn a metal in a turbine and then capture the exhaust so it's zero CO2, NOx, SOx emissions out of the system? Would that be relevant for this potential program?
I believe it would.
Comment and a
I say
question.
that cautiously because the devil will be in the detail. But notionally, yes, that would be acceptable.
I think it's overly constraining to target zero NOx. Why not just meet current and future NOx standards, even with hydrocarbon fuels?
Well, if you have a proposal that you think can achieve everything except maybe that, we would look at it. But our metric at the moment says zero NOx.
Next question, is the power output in kilowatts the net output from the battery system after subtracting any usage for cooling, etc.?
Yes.
All right. I think I've asked all the questions so far that are technical questions. There were a few related to the FOA, which we don't need to answer at this point.
If a FOA is issued here, there is a formal process whereby questions can be asked about contract language or contract meaning and all that. So we would defer to that, and we're not going to answer contract questions on this call.
Yes. So if you have any other questions that we have not asked yet, please type them in chat again.
And as I said, one-on-ones are available for those people who want to have more intimate conversations with us.
Okay, so question is, can one company submit multiple proposals in the same track in multiple tracks?
Can't tell you, but the normal practice is, yes, you can submit as many proposals as you like.
Are you also looking at system level simulation and analysis for these new battery technologies integrated into aircraft or marine vehicles?
In the deliverables, the system modeling that was mentioned as part of deliverable 1, yes, that kind of modeling would be appropriate for that particular deliverable.
An earlier question seemed to open the door for hybrids, including engines and thus hydrocarbon fuels, but I believe that is out. Please confirm.
Yes, I confirm. If the solution has hydrogen carbon bonds in it, we're not interested. Or I should say the fuel. If there's a fuel that has hydrogen carbon bonds in it, we're not interested.
Will these slides be available before the one-on-ones?
No.
Are the one-on-one meetings scheduled already? I received a confirmation, but I don't know when it would be. Thank you.
Somebody else needs to answer that question.
I think we have scheduled all the meetings that we were requested, but please send a note again if your meeting has not been scheduled, and we will look into it. What timing are you targeting for the availability of this energy storage technology?
Well, I'm not sure that's a really specific question. You know, I think this is a combination between how aggressive do we need to be and how realistic must we be. So I would say, based on my experience, I would be disappointed if we weren't demonstrating this in vehicles and vessels in 10 years' time. So serious demonstration in 10 years' time, I believe, is a reasonable objective. In terms of widespread adoption, it's obviously going to be sometime after that.
Right. What beginning TRLs are you looking at? What is the level of acceptable minimum preliminary data?
Good question. We get into internal conversations about the value of TRLs. This isn't about research, fundamental research. This is about things that at least have some level of possibility that's been either shown through good modeling or good experimentation or good scientific rationale and argument. That's what we like to see in proposals in general. Generally, if you were to do a distribution of technology readiness, mostly technologies in an ARPA-E program are being taken at TRL 2 or 3, and as part of the project, we're trying to move them from 2 or 3 to 4 or 5. So that I'm saying is a generalization of what ARPA-E tends to be looking for. But there are lots of exceptions to that rule.
Okay, so another question is, if the proposed solution meets the metrics, why does it matter if a working fluid is in a reversible system, for example, has a hydrocarbon in it?
It doesn't matter if it's a working fluid, it just can't have emissions. So yes, it can be part of the system as long as it's not getting outside. And that certainly maybe wasn't clear. So if it's a working fluid, that's fine. If it's being combusted or being released in any way, then that is not acceptable.
Since mechanical packaging and thermal management are included in the denominator of the metrics, how much design/modeling is expected to be included in the solution concepts and reporting?
I would say you're going to have to wait to see if there's an actual FO on this to answer that question. What I said earlier in the presentation is we expect 80% of the effort in any proposal to be in the phase 1, and we're accepting that phase 2, which would involve all of that system design and system modeling stuff in detail, isn't going to be known in detail until prospective teams have done some work as part of phase 1.
Thank you, Halle. So those are all the questions we've been asked so far.
Sounds good. We once again thank you for everyone for attending. We are starting one-on-ones at 1 o'clock today, so I've actually got some time to get some lunch, which I'm very thankful for. And thank you, Apoorv, and also Sean, who was on the call, for your support, and other ARPA-E people who would have attended this meeting. So thank you all. We'll see where this ends up.